Um, so yes, this isn't my regular seminar. This is the topic I would talk about on a blackboard or for a sort of informal talk. So I am extremely happy to be interrupted. And there are some concepts which, at least when I've given this in the past or talked about this topic, some people have struggled to get. And to be fair, I struggled to get it until I started looking at this 6 months ago. So please do interrupt me. This talk is going to be geared completely around this paper. If you want to follow on and try and avoid asking things, get this paper up in front of you. Whenever I give an equation, I will link with that equation number to a number I give will be the one it is in the paper. So if you want to know where it came from, more detail about it or anything else, read the paper while I'm talking. It'll be more instructive than reading your email. Okay, so this is the last fun thing I did before I got sucked into teaching an admin this term. I did this over the summer with Oliver Friedrich, who's a very, very good postdoc in Cambridge, and Eleanor Selentin and Alan Heavens. And we all got together because we didn't understand what was going on in this area. And we managed to work it all out, which was quite nice. I should say this work follows on from some work I did in 2014. And the original idea behind this was I was looking at BOSS data as part of the team. We were trying to fit BAO to those data. We had fitted our pipeline to mock catalogs. And from those mock catalogs, we got a distribution of errors, a distribution of errors and a distribution of best fit points. But the distribution of those best fit points looked nothing like the error we were deriving on average from those mocks. So there was clearly something going wrong about how we were interpreting our errors and what we knew about our errors. And as I say, I did some work on 2014 on this, but this is actually what I now understand is actually what I actually did in 2014 was a little bit naive. One would hesitate to use the word wrong, but it was just naive. And now I think I know what I did and why I did it a little bit more. All right, that's the preamble. That's kind of like the introduction. Let's get into this. So, as you probably all know, there are two common ways to characterize our uncertainty. When somebody tells you the measure of the Hubble parameter with an error bar, as physicists, we go error bar. Oh, good, I know what a 1 sigma error bar means, but there are actually two ways to create those intervals which have a coverage probability that are in common usage. And they lie at the heart of the difference between a Bayesian and a frequentist approach. So a Bayesian scientist would say, okay, what I actually want is to define a credible interval. This is an interval that, given the prior, which is all the information I knew before I created the experiment, and the likelihood, which is the information I've got from the experiment, I can create a posterior. And now the credible interval contains a certain coverage probability obtained by integrating under that posterior. So if you have an error bar, which is a 67% error bar, you would say, okay, I've measured omega m to within plus or minus 0.1. So your range of omega m of 0.29 to 0.31, for example, you would say that I'm pretty confident I have 67% probability that the truth lies within that region. That is what Bayesian scientists would call a credible interval. You can also define a confidence region, which is a frequentist definition. And that supposes that now there are a large number of scientists in, infinite parallel universes, all also performing the experiment. And now you want to construct an interval. It may or may not be the same interval, depends on the coverage probability, but let's suppose you want a 67% coverage probability interval within which 67% of those scientists in their infinite parallel universes would have obtained, or at least, the truth in all those universes lies within your interval. That would be a confidence region. It relies on repeated trials. It doesn't rely on any prior. Basically, what you're doing is you've got these repeated experiments, and it's the idea that within these repeated universes, how many times does the truth lie within your interval? These are two very different things. They don't have to agree, but in most situations that physicists deal with, they do agree, because we normally assume uniform priors, a linear model, the Gaussian likelihood, And under those circumstances, the coverage probabilities of these two intervals do agree. So you can define one interval, omega m between 0.29 and 0.31, say, and then the coverage probability of 67% applies to interpreting that interval as both a credible interval or as a confidence interval. And then you're free to hand wave and do the physicist thing and say, hey, look, I've just got an error bar and I'm going to interpret it how I like. But in general, it's not true. And what's kind of interesting is that if we derive a covariance matrix with which to fit data from simulations, then this isn't true. And this is the root cause of the problems we had back in 2014 when we were trying to fit BOSS data. Okay, any questions before we go on this? All right, it's quite important everybody get this aspect. Okay. So what we have often is a situation where we estimate a covariance matrix from mocks. So if you have 100 mocks, NS equals 100, then you would estimate your covariance matrix and your estimate of your covariance matrix for a set of data that you want to fit, be it a galaxy power spectrum, a correlation function, a luminosity function, whatever you're fitting your model to. This would be the covariance of those data that you would use in your likelihood. NS is the number of simulations you have, and it's basically how do those simulations vary around the average that you recover from those simulations. Now, it turns out that this is a covariance matrix, which is itself a random variable. You can consider that it's drawn from a distribution. If you chose 100 different simulations, then you would have got a different covariance matrix, and you can see that the covariance matrix itself is itself a random variable. Just like you have a data point drawn from a Gaussian distribution, you can actually have a matrix drawn from a matrix distribution, and in this case, it's the Wishart distribution. If you look up on Wikipedia, there's a very good page on the Wishart distribution. In fact, if you do jackknife realizations, you also end up with a Wishart distributed matrix. It's a pretty common distribution for these sorts of covariance matrices. The domain it's over is all positive definite matrices. In this case, it makes sense to consider that your 100 simulations should actually be considered data, and the model should also include the true covariance matrix. So in effect, you have the data, which is, let's say, the power spectrum you've measured from your galaxy survey. You have the mocks with which you've calculated or estimated your covariance matrix S, and then the model you want to fit to those data is mu, the model, and sigma, capital sigma, the true covariance matrix. In this case, as I say before, credible intervals and confidence intervals do not in general match. So here's an example of a simulation that Oliver Friedrich did when we were doing this work. What he did was he simulated, completely simulated dark energy survey-like cosmic shear data vectors, including order and cross correlation, psi plus minus. The details really don't matter. These are just correlation functions that you're going to treat as your data. And then he calculated 650 simulations of those data, and from that calculated a covariance matrix. Now, he had 450 data points, so actually 650 simulations weren't quite enough to really well determine the covariance matrix, and so we see a larger effect here. So if you look at the red shaded regions, these would be confidence intervals, credible intervals that you would obtain in sigma 8 and omega m from these data, and the three different realizations. It's fake data, so we can imagine doing the experiment 3 times and creating 3 different lots of fake data. And for each one of these plots, then there are also 3 different realizations of simulations from which the covariance matrix is drawn. So the red shaded regions are what would happen if you actually had the true covariance matrix. And there, basically the Bayesian scientists would say within this dark red region, I'm confident 67%, I'm 67% confidence that the truth lies in there. The frequentist would say, okay, if I now repeat this not 3 times, but 1,000 times, then 67% of the time, this dashed line, which represents the truth where the simulations were drawn from, that will lie in the dark red shaded region 67% of those 1,000 runs that you're doing. So that's the fundamental difference between credible intervals and confidence intervals. It's this difference between being confident with the prior and the likelihood compared to how many times does the truth lie in your basically region. So there are different ways of calculating the posterior when you've got your fake, or it's not a fake, but your estimate of your covariance matrix. And these are shown by the open contours in orange and blue, and I'll explain what the orange and blue are later. But in general, when you haven't got this true covariance matrix, you've got your estimate. It is no longer true that this dashed point, the point marked by these dashed lines, lies within your confidence interval, the coverage probability number of proportion of the times that you expect it to, because we're now in the situation where this credible interval and confidence interval don't have the same coverage probabilities necessarily. Okay, any questions? All right, I was told you lot ask questions all the time, so I'm beginning to get a little bit paranoid, but I'm going to carry on. Okay, so this is a common problem, and it's been known about for some time. One way of thinking about it is that for any covariance matrix drawn from a Wishart distribution, like S was, when you invert it, you get a biased estimator of the true inverse covariance matrix. So the analogy here is that if you've got a series of data points, let's say I've given you 10 data points and I've asked you to calculate the mean, you would just average them, and that would be fine, and that would be an unbiased estimate of the mean. But if I wanted you to calculate the expected value of 1 over x, you wouldn't just take 1 over that mean that you've calculated. You would take 1 over each of those data points and average that. And that's because 1 over the expected value of x is a biased estimator of 1 over x. The same is true for these matrices. The Wishart distribution is a skewed distribution. So the inverse of S is a biased estimator of the true inverse covariance matrix. This has been known for a while, and you can correct it by, rather than inverting S, you can invert H times S, where H, and now I'm thinking about Hubble parameter, so I should have chosen a different variable, but H is, in this case, not the Hubble parameter, it is ns minus 1 over ns minus nd minus 2, where nd is the number of data points you have, and ns is the number of simulations that we had before. This is commonly called the Hartlap factor because in astronomy we name things after the astronomers that first rediscovered them from some other literature and brought them into astronomy. It actually dates back to 1967, but the Hartlap paper that introduced this in astronomy, that has 625 citations, which suggests that 625 people have at least thought about using this as a way to correct for this problem where you've got an estimate of the covariance matrix and you want to invert it before doing your likelihood in order to unbias your likelihood.
Do you mind if I ask a question?
Yeah.
So S is a matrix which contains a bunch of entries which are drawn from a distribution. Is that right?
Yep. Yep.
And then what you're saying is you multiply this matrix by a scalar, which is related to, and then it becomes, and it becomes an unbiased estimator. That
when you now invert it, yes.
Okay.
It's an unbiased estimator of the true inverse covariance matrix.
Is there like a simple reason for why if you just multiply a matrix by a scalar and then invert it, all of a sudden it becomes an unbiased estimator where before it was a biased one? Because that to me, like, I mean, that's very counterintuitive to me at least.
Yes, and I think that is special to the Wishart distribution in this case.
Okay. Okay.
Okay. So there's no reason why this should work, and it doesn't follow particularly from a Bayesian or a frequentist viewpoint. So let's do things properly. And actually, this is a problem that has a long history in statistics. So this is the equation that you've all seen before, Bayes equation. The posterior is the likelihood times the prior. What's different here is that on the left-hand side of the posterior, we've got the model and the true covariance. And on the right-hand side, we've got the data and the estimated covariance. The likelihood is obviously the two the other way around, and we need a prior on the model and the true covariance now. So we're going to stick with a uniform prior on the model, but for the true covariance, we're going to look at different forms of prior. Now, we're not actually interested what the true covariance is, so ultimately we're going to marginalize over it. And so the posterior that we're going to use and plug into Cosmo MC or whatever MC routine you want to explore your posterior and get your cosmological constraints out, that is f of mu given x0 and s, where x0 is the data. Okay. So choice of prior. It turns out, statistics literature, there are many different choices of prior that people have advocated for different reasons. This Sonnenberger paper, reference from the paper that I wrote, lists a number of them. There's the Jeffreys prior, there's the independence Jeffreys prior. There are other choices given there that other people have suggested going way back in statistics literature. They all tend to be of the form of the modulus of the determinant, by basically the determinant of the true covariance matrix to some power, where that power depends on the size of the matrix. And Salentine and Heavens in 2016, they wrote a very influential paper where they used this prior, the independence Jeffreys prior, in their Bayesian analysis now. So 151 citations suggest that 151 people have at least thought of doing this method in this situation. If you work through it, and we're already up to equation 14, because I'm not going to go through the maths of the derivation for you. It's there in the paper if you want it. It's kind of actually kind of neat. But ultimately you plug in the fact that the S is drawn from a Wishart distribution, you'll get Gaussian data, the prior you've got given there from the formula that I showed before, plug that in, do the integral marginalizing over the true covariance matrix, and you find out that f of mu given x0 comma s, which is what you want as your form for the posterior to plug into Cosmo MC to tell you what you know about the model given the data, that is no longer Gaussian. It has a multivariate t distribution. Wikipedia multivariate t distribution if you want. There's another good page on that. It's very common in statistics. You have a scale matrix and some degrees of freedom, but it's a form, and that form is given here. Basically, rather than the Gaussian e to the minus half chi-squared, you instead have 1 plus chi-squared to some power, where the power depends on ns. So all you have to do in Cosmo MC, if you want to change to this form rather than a Gaussian, is change the line that says e to the minus half chi-squared and put in 1 plus chi-squared to the minus ns. Ns over 2. Interestingly, because Wikipedia also gives the covariance of the multivariate t distribution, you can read that off for this distribution. 17 Heavens didn't do this, but you can do this. And then that equals h times s. So basically, multiplying your s before you invert it and then using a Gaussian likelihood is in many ways just a Gaussian approximation to doing this full Bayes derivation and ending up with a multivariate t distribution, which is kind of interesting. And it explains why there's probably like 100 papers saying, we looked at doing the Hartlap factor, we looked at with a Gaussian, we looked at doing Salentine and Heavens, we found absolutely no difference in the constraints we got out. We're comfortable carrying on with whichever one takes our fancy at the time we wrote the paper. All fine and good, but it's a little bit nagging that there is this choice of different priors that you could use in this situation. And as we will see later on, the errors that you get out doing this method still don't match that distribution that you got if you were repeating the experiment. And so let us move on. And this is where start to get the bit that we did that was new. So what we did is realize that if you now just put a free parameter in your prior, so now rather than the particular form of the independence Jeffreys prior that Salentine and Heavens picked, you allow your prior to have this more general form. This ns minus nd plus 1 just actually simplifies the equations later on. You should just think of this as being a free parameter, so a free power law on the determinant of the truth. The derivation actually works exactly the same way, and you still end up with a multivariate t distribution posterior. the scale matrix depends on M now, and the variance of your posterior, that's the width of the posterior for your model data pair, depends on M. So this is perfectly standard and normal in Bayesian analysis. Bayesians don't mind this at all. Actually, everybody's kind of like Bayesian frequentists. Nobody's one or the other, but there you go. But, you know, as expected, the prior and choice of prior directly leads to the size of your credible intervals. So if somebody from an experiment where they've calculated the covariance matrix from a set of simulations tells you, aha, I've measured with 67% credible interval on omega m being 0.29 and 0.31, you immediately go, have you indeed? But what prior did you assume? Because that's vitally important for that error bar you've just given me. Because you could have picked a very different prior and got a very different error bar, which is always a little bit disappointing when you're spending €1 billion or something on an experiment, and then the answer they give you is dependent on a choice made in a very short meeting. Okay, but that's standard in a Bayesian analysis, and it's okay. So, to carry on, we need to get a little bit more complicated. As you see, we're jumping now from equation 21 to equation 37. But let us suppose now, instead of just fitting a model for a power spectrum to some data, we instead have a model that is parameterized. So now these parameters, we're really thinking of them as cosmological parameters. And our data vector is, for example, a power spectrum with baryon acoustic oscillations that we want to fit, for example. In this situation, everything gets a little bit more complicated, but we can still take that posterior, the multivariate t distribution posterior, and we reduce it now down to a distribution around the best fit. To simplify this and do this, we have to assume that we're fitting a linear model. So our power spectrum is just some linear combination of the cosmological parameters. So it's a very big approximation. But when you do that, plug it into the equations, then you find that your posterior distribution around the best fit for those parameters is written as some complicated function involving S, the data, S in the inverse covariance, in the Fisher matrix, the inverse Fisher matrix, G, which is just some linear combination of X, and so on. But you can write this down, and if in this situation, if you're fitting a linear model to a power spectrum, then you wouldn't need to run CosmoMC, you wouldn't need an MCMC to explore the posterior surface. You know you would end up with this kind of distribution around it with this particular variance. Okay, so carry on. Now let us go a little bit further and suppose that there's an infinite number of scientists doing this. They each pick a different X0, they each pick a different S. On average, what do they get? Well, on average, these are the errors they get for those cosmological parameters. So this is now mixing together Bayesian reasoning and frequentist reasoning, because we're now saying, what would 1,000 different scientists in parallel universes, all of them Bayesians, on average get as their credible interval? This is the variance of the distribution from which they would determine their credible intervals. All right. Pausing for questions again. There are none. Okay. So let's have a look at the frequent. Oh.
Aren't you, when you're saying averaging over multiple physicists, aren't you implying a prior there too? Like,
yes.
What prior do they choose there?
They've all chosen the same prior.
Okay.
Yep. So they're all Bayesians. They've all decided to go with, for example, the independence-Jeffreys prior. Then for that value of M, this is on average the variance they would get in their posteriors.
Okay. Thanks.
Okay.
Can you hear me?
Yep.
Back when you introduced the Hartlap factor, you had the N and D, and then one of the bullets said N theta, the number of parameters, but it actually wasn't in that factor. It's only coming in now with the model.
Yes, good point. And I will deal with that later, but it's come in here because we've suddenly considered this model, and the model has n theta parameters, and that the variance that we get out depends on the number of parameters here. This is actually a different calculation from the Hartlap factor, which was simply debiasing the covariance matrix. Here we are doing something that's gone beyond that, and we're actually looking at the posteriors themselves that we get back out.
Yeah. And then you actually know that inverse of the Fisher matrix, because sigma is supposed to be the real thing, isn't it? S is the estimate.
This is the equation 26 is the definition of the Fisher matrix. So it's got a subscript S, which means it's the Fisher matrix calculated with the estimate.
Right, but what about in equation 46? What's the sigma mean?
Oh, yes. Yeah, so this is just on average what they would get, right? So you're right that if you don't know what the expected value is, then you couldn't get this. But remember, what we're doing is we've got 1,000 parallel universes, each containing a Bayesian scientist doing exactly the same experiment. And so you should hopefully see that on average, they will get, because they've each calculated a different S, an answer that depends actually on the truth.
And so that prefactor is just debiasing the inverse.
In a sense, yes.
Okay, thanks.
Okay. So let's move on to a frequentist perspective. Now we've got our large number of scientists in parallel universes, each performing the experiment, and they've each got a best fit answer for what the parameters are. And we're looking at the distribution of those best fit parameters that they've all obtained. It's a linear model, so you can write down what that best fit solution is. So in the same way as I ask you to take the mean of 10 numbers, or what is the mean of these 10 numbers, you are not trying to fit a model with a flat line to all of those numbers and running an MCMC to explore the posterior. You can just write down it's the average of those, and that's the maximum likelihood estimator. This, in the same sense, is in our situation in a linear model, that same best fit. So each one of those scientists find this best fit. We can ask what the distribution is of those best fit values, and you can write that down. This is a calculation actually done by Doddleson and Schneider in 2013, and they found this value of the best fit. Again, it depends on that inverse Fisher matrix of the true covariance matrix, and there is again a prefactor here. Because this is a frequentist estimate of error bars or confidence intervals, there is no dependence on the prior, so you can immediately see that there's a difference between the example that we had before and now this frequentist viewpoint of what your quote unquote error bars should be. But, and here's the thing, you can make them equal by choosing a particular value of M. So what is happening here? Well, you're using the Bayesian analysis method as a way to create, in a sense, a confidence interval, and you're equating the coverage probabilities of treating that interval both as a credible interval and a confidence interval. So if you choose a particular value of M, which means choosing a particular prior for the true covariance matrix, you can go back to your state as a physicist where you just have error bars and you can interpret them how you like. Sorry, I didn't actually read this slide to see if that's what I meant to say, but I think it is what I meant to say. So, and it's a formula involving NS, the number of simulations you had, ND, the number of dimensions of your size of your matrix, and N theta, which is the number of parameters. What does this mean? Well, in Bayes' theorem, as we discussed before, the choice of a prior is literally that, just a choice. Question, Juna.
Yeah, if you go back a slide, I mean, it strikes me that something powerful here is that you kind of have to, you kind of get a sense of how many simulations you want to do to actually converge on this M match quantity, right? Because if you are only doing a few, then you're getting a huge error in that. And so and I apologize, I haven't read your paper in advance, but are you finding that number, like, is this a way to guide that number?
Yes,
so that
absolutely.
Okay.
Yes. And as you can, I'm going ahead towards the end of the talk, but you can always do better by having more simulations. And if you have an infinite number of simulations, you go back to the original problem where if you have the true covariance matrix, which we're assuming you get after an infinite number of simulations, then in that case, you automatically have this matching property and you automatically have the smallest error that you can possibly have. Whereas in this case, when you have a finite number of simulations, your error bars increase, but you'd still have this matching property if you apply this particular prior.
But there's some kind of threshold that you can say, you know.
So
yeah.
I'm going through to an example next that will look at that in detail. So Alan made me promise to put this in. So if you use an independence Jeffreys prior, there's nothing wrong. So if you just used his paper and with Eleanor before, then you haven't done anything wrong. You've derived a cosmological parameter, which is correct. It's just that your prior has potentially brought in some information, or at least more information than using this matching prior, because this matching prior in general is more conservative and it gives larger credible intervals. Okay, so let's go back to this series of plots that I showed before, and now hopefully you should understand them a little bit more, because the green open contour, the orange open contours are the independence Jeffreys prior. So these are what you would get from your experiment, assuming that independence Jeffreys prior, which if you remember is rather like, in terms of the variance of the posterior distribution, rather like having a Gaussian posterior and multiplying by your Hartlap factor. And if you use the matched prior, then you get these blue contours. And you shouldn't infer anything from just 3 examples, but hopefully you can see that there's a better chance that this dashed cross line, which marks the truth, will, after a large number of realizations, fit within this smaller confidence interval, credible interval, 67% of the time, and that's more likely than this orange one, which just looks a little bit too small. And so because these are simulations and because Oliver could just run these off very quickly, we didn't just do the 3 of them, we did thousands of them. And this is a plot of the fraction of times the truth lies within your credible interval against the number of simulations that you have. So NS is given on the x-axis. This is for ND, number of data points of 450. So if we push down to only 500 simulations for 450 data points, then we are really, we should know we don't have enough simulations. And indeed, if you do that, and you use either the Hartlap factor with a Gaussian posterior, which is these orange crosses, the independence Jeffreys prior with a t-distribution posterior, then you get these values down here. So for example, if you did your experiment, you had a data vector that's 450 size long, you used 850 simulations, and you just did the Hartlap factor, or you did this independence Jeffreys prior, then in fact you would find that and you did it repeatedly, I should add, then you should only find the truth lies within your interval like 40% of the time. But if you use this match prior, then you're matching the coverage probability when interpreting the interval as a credible interval or a confidence interval, and therefore this test, which is the how many times, what fraction of the times does the truth lie within your interval, which is defined as basically your confidence interval, that matches from the credible intervals that you've derived in this situation. And this on the left is it in the 68%, the 1 sigma, if you like, and on the right, it's the 2 sigma, 95% confidence interval. So you can see this matching prior is doing its job. That's all these plots tell you, is basically that if you use this matching prior, you do your Bayesian credible interval, you do it many times, then you'll find that it can also be interpreted as a confidence interval, as it should do, because that's how it was derived. Any questions on this? Hopefully you can see the Juna's question earlier, you can see how the number of simulations affects this interpretation of these intervals.
Will, I do
Yeah.
have a question. So in this picture, the covariance matrix is also a data point. So I guess the evidence should also change, which I think would be the main difference between making 500 and 1500 simulations. Is that something you have explored?
We did not explore that, no. We did not look at how this affects the evidence. But yes, it will change and it will, yeah, it will be affected.
Right, so it should improve ideally for more simulations, right?
Yes.
Perfect.
Basically everything, as long as you use millions of simulations, everything is fine. Unfortunately, you'll never get the time to do that.
Yeah, I wonder, because if I look at this plot, there's no reason to use 1500 instead of 500 simulations, right?
No.
The moment you do the t-matching.
Not if you have 1500 simulations that you're happy with. And I will talk at the end about ways that you can get around all of this.
Okay.
So what was going wrong with the Hartlap factor? Well, as I said at the start, in a sense, it's there to debias the covariance matrix estimate, and the inverse covariance matrix, which is what you use in your chi-squared, is debiased if you include this Hartlap factor in it. So what's happening? Well, in a sense, you are debiasing your likelihood by using the debiased inverse covariance matrix. Your posterior is, in a sense, unbiased. So why is that not enough? Well, the same thing is happening in 17 and Heavens. That gave exactly the same variance. And I think that shows a highlight of what's happening, is that this independence-Jeffreys prior is actually debiasing the posterior in the same way that the Hartlap factor is debiasing the inverse of the covariance matrix. So they're all, in a sense, giving you a debiased posterior. But when you actually calculate parameters, use your posterior to determine parameters and their error bars, actually what you're doing is you're going from the posterior through to error bars. You're kind of like doing that inversion again. You're going from an inverse matrix in your posterior to a non-inverse matrix. You're warping it a little bit. You're putting it in a Fisher matrix context, but you're doing that to go through to your model parameters. So I actually think what's happening here is that the way the independence-Jeffreys prior has been derived and the way the Hartlap factor is derived, it is correcting the posterior and giving you a debiased posterior. But then that doesn't give you debiased errors on the parameters that you derive from that posterior. There's another step, another half of the picture, if you like, that says, actually, if I now want to go through to parameters, here's what happens. And that's what's coming in with this new derivation and this new prior choice. So to summarize the method, instead of using e to the minus a half chi-squared, you should stick with the multivariate t distribution. You should use 1 plus chi-squared over ns minus 1 to the minus m over 2, where m is given by this complicated formula of, depending on the number of simulations you have, the number of data points you have in your covariance, in your data vector, and the number of model parameters you're fitting. But other than that, it's a reasonably simple change in your MCMC routine or wherever you're coding up your posterior. Rather than one line, you're just going now to 4 lines of code. Yeah, another question.
Yeah, so it looks like you've got 3 levers here, N theta, ND, and NS. You can, I guess you don't have a lot of control over the data, ND, but you can crank up NS. And you can try and have a simple model, I suppose, to control N theta.
Yeah.
But these levers, the playing with them, must, in some limits of some lever, lead to one of those priors that you flashed up before. You had a different choice of.
Yes, that's correct.
So.
And in fact, if you, sorry, Karen. Okay, if you go back to Sonnenberger, there are actually some of the derivations of different priors actually work in some of these limits. So when you have, for example, n theta equals 2, I think there's, I forget the name of it, that one of the priors actually matches into this matching prior, and it actually fits with the rationale that was given for that prior choice. So this prior could be considered a broader class of prior that encompasses that one. I would argue that these aren't really free parameters you can tweak, right? In the sense of once you've set up the experiment and you know how many bins you're going to use for your power spectrum, you know you're going to fit it with a 6-parameter lambda CDM model, and you can only afford the computer time to get you 2,000 simulations. That is kind of fixed. You're always going to want as many simulations as you possibly can get. You might worry, though, that this prior choice depends on the properties of the data and the problem. And with your perfect Bayesian hat on, you might say, actually, your prior should be determined before you do your experiment. It should be what you know about the universe without having done your experiment. So you shouldn't know ND, NS, and N theta at all. Now, this is actually called an objective prior. I've run this paper past a lot of statisticians, and none of them are in any way worried about this. You don't know the actual values of the data that your experiment has given. You only know your experimental setup, and nobody seems really worried about that at all. It's quite common within Bayesian statistics, and generally it's considered okay. There is a question about the multivariate t-distribution, which makes your posterior, I mean, it changes the form of the posterior. This whole matching has been done on variance and not on the form of the posterior. So in principle, you could pick a prior that wasn't a power law of the determinant of the true covariance matrix. You could pick a different form for that prior, and you could pretty much get whatever distribution you wanted. It would still, if you wanted this matching property, you would have to at least match the variance and other things as well. And in fact, if you look in the stats literature, matching priors, there is quite a lot of literature on them. They tend to be matched in a way that matches both the form of the posterior as well as the width. So there's nothing particularly special about the multivariate t-distribution, except that when you use this posterior, you know exactly what's got into it. You've got this prior, it's a power law, you know the power law index, you know exactly what you've done and plugged in to do your analysis. So it has that nice property. If, however, I'm going to come to your question in a minute, June, I just want to finish this train of thought. If, however, you really, really wanted to stick to a Gaussian posterior, then you can determine the Gaussian posterior that has the same matching variance as this t-distribution, has this same property that you should get the same 1 sigma and 2 sigma confidence and credible intervals. Then actually, when I said at the start, I'd done some work on this in 2014, that is what I derived. I didn't know what I was doing then. All I wanted to do was determine a Bayesian method that matched this frequentist idea of the distribution of best fit points that I got from the mocks. And I went through the maths just to determine the variance, and I plugged that into a posterior to get that variance. It wasn't elegant, but it actually gives pretty much the same result as we're now advocating with this new matching prior. So in that sense, I'm quite pleased, but obviously I wish I wasn't quite so naive back in 2014, but there you go. What I like about this is not, you know, you can go away and use whatever prior you like. Everybody wants to be Bayesian these days, as long as you say what you've done and give some rationale why, all good. What I like about this is now we've worked out how it all fits together, how the Celentine and Heavens approach matches with the Hartlap factor, matches with what I'd done previously, matches with Donaldson and Schneider. Previously, we had all these different approaches in the literature, and there wasn't a clear way that they all came together and gave one coherent picture. But now I think we've got that picture. It required unpicking error bars into credible intervals and confidence intervals. It required this idea of matching prior, but now that's all there and available for people to see in a slightly different way how it all works. Okay, Shuna.
Yeah, so I feel like this does have like this sense of having your cake and eating it too, which is nice. But I guess one question that I have really, and I know the statisticians aren't bothered by this, but part of being, you know, super flexible or, you know, in the prior is so that you have a little bit of models like selection with your parameter estimation. And by that, I mean that you can see weird things in the data in the posteriors that kind of tell you that things aren't quite right with your model. So there's some sort of discovery potential. And I wonder if that is still captured in this matching case, because and the way that usually manifests is these like tensions that you see in the different parameters or something like that. And I wonder if those tensions are kind of automatically eliminated with the matching. And it's not I don't have a well-formed reason to think that that would happen in this case, but it does seem to be that's sort of my fundamental concern. That would be the same fundamental concern that you have at bullet point 1, which the statisticians don't worry about, that like we kind of are using the posterior distributions partly as discovery tools and not just model estimators. Like when we think about the types of things we want to do with next generation surveys, we want to be cautious that we're not foreclosing any of those kinds of like very small effects that might be telling us something. So have you thought about that at all?
Yeah. So I actually think if you want to estimate tensions from an experiment where you have this estimated covariance matrix in this situation, you certainly do want to do it with this matching prior. On the one hand, it is conservative in that it's larger. But on the other hand, when you're interpreting tensions, one tends to be interpreting them in a frequentist view, which is how many times would this occur within a context of people in parallel universes doing the experiment. And that is a posterior type of comparison, a frequentist type of comparison, which requires a confidence interval. I don't think there's anything here that is going to preclude discovery of tensions. In a sense, all you're doing is putting in a prior that has this matching property and being more conservative in what you determine to be a tension or not.
Right. Okay, interesting.
Okay, that was actually the end of my talk. So keep asking questions, everyone. Okay, there's another.
Yeah, it'd be interesting to be the fly on the wall in your discussion with the various statisticians. So maybe this would come up. They say, great, you've got this matching thing that makes frequentist and Bayesian descriptions agree, but I'm a Bayesian of some flavor, and that's really not the prior that I would pick. So do you get into discussions like that?
We did get into a lot of very interesting discussions, yes. There were a number of statisticians. I was expecting almost all of the statisticians to be advocating Bayesian methods only and to be saying, right, you accept this, it's a Bayesian method. There's nothing in the choice of prior, you can just choose whatever prior you want. But actually, all of the statisticians I spoke to, and this is not a representative sample at all, they just were like, yeah, you can do things in a Bayes way, you can do things in a frequentist way, easygoing kind of thing. And actually, some of them I said to this, they were like, why are you faffing around with all this? Why don't you just do a frequentist analysis? And then, and then we said, well, most of the tools are actually simplest. If you do a Bayesian analysis, we're all set up to use Cosmo MC, we're all set up to explore a posterior. We're not actually set up to repeat the experiment using mocks many times and try and derive our error bars from that. So from that point of view, this is kind of nice in the sense of you can keep with doing all of your Bayesian things, you can keep with doing your MCMC exploration of the posterior, and the answer you get out has this dual interpretation.
Great, thank you.
So if nobody's going to ask a question, I'll answer the question that I think should have been asked. How do you solve this? How do you not have this issue of basically, suppose I've got a finite number of simulations. I only get the computer time to run 1,000 simulations. What do I do? Well, there's a number of things you can do. You can reduce the size of your data vector. So you can reduce the number of bins you put your power spectrum or whatever it is into, in the limit that you still retain all the information needed to distinguish between the models you need to distinguish. So you could imagine doing some sort of data compression, Kahun-Louvre type data compression that kept the information that you need there in your data vector. As long as you reduce ND in that way, then your simulations count for more, if you like. One thing we found that was interesting was that if you use the multivariate t-distribution, data compression doesn't quite work like it does in Gaussian cases. If you use the example of calculating the mean and saying that's a compressed data set for calculating the mean, and I've got all of the information about the mean, that's not quite true if you've got this multivariate t-distribution, and that's in one of the appendices of the paper. Other things you can do: increase the number of simulations, obviously, but you can also introduce extra information into your covariance matrix. If you know in some sense it should be smooth, if you know that it should have a particular form, or you have an analytic model for it that you're not sure and you want to combine with your simulations, you can do anything like that that improves the covariance matrix beyond, go all the way back, this naive formula, equation 1, then that will improve the errors that you get and make the fact that you've got a finite number of simulations less important. If you're feeling brave and you think there's a full analytic way of determining your covariance matrix on your luminosity function, power spectrum, whatever it is you're fitting, then all well and good. Then you've got none of these effects. That is not drawn from a random distribution, and you can go away and do your standard uniform priors on the data parameters and not have to worry about interpreting things in these different ways as credible and confidence intervals at all. The only issue is if your analytic model itself has errors, then you are introducing an error into the error you determine from the fitting the data, if you like, and you do have to be a little bit careful because now you don't have that handle on statistically what's happening. If you do this naive approach with the simulations, at least you know statistically exactly what you've done. But if you start introducing eigenvectors and smoothing the matrices or using your full analytic model that you're not quite sure about bits of, then you no longer really have this handle on it statistically exactly what you've done. And there may or may not be another systematic error on your data in the end. Sorry, on your model parameters in the end. June, another question.
Yeah, so this is, I mean, similar to my question earlier, and you know, have you applied, if you think about something like DESI or you think about PFS or something, and you think about these priors or any future program, like, have they done enough simulations to, like, in other words, like, how bad are we off? Because it's a lot of simulations. I mean, so essentially, and the whole like, okay, well, we can bin the data. I mean, that's just like a sin. Binning is sinning. I mean, so I mean, it's telling you that you don't have the realizations that up to your data fundamentally. So whenever you're in that situation, it's like a 5-alarm fire to all of the supercomputing centers, right? Like, this is a crazy thing to do. Please give us more computing time. But how are we, like, as the, like, in terms of these different collaborations that we're kind of counting on to give us power spectra or other things, and to figure out how are they doing?
So okay, that's a good question. So we're not there yet, is the answer. I have actually well, okay, so there are two things. One, quite a lot of work has been done on this using things like the Hartlap factor as suggesting the size of the error that's introduced by having this. I would say they were perhaps not as conservative as they should have been, because now our error bars should be a little bit larger. But in Euclid, for example, we have a stipulation that this kind of error should contribute 10% or less than the standard statistical error because of the realizations, cosmic variance, shock noise. And so people have been calculating the number of simulations we need. And yes, it is relatively high. That means we'll have to use mocks and do smoothing methods and other things as well. I have now given a version of this talk, a very close version of this talk, to groups in DES, to groups in DESI. I'm talking in Euclid in a couple of weeks' time. So I'm getting the word out, and it's nothing new, but what I think these groups are liking is actually more the understanding of the problem now, rather than just plugging in the Hartlap factor, because that's what everybody does before. It's actually the understanding of the overall picture that's happening. So if there's another survey that I should give this talk in and explain how error bars are determined, then let me know.
No, I just have like this unsettled feeling about the number of simulations that these groups have done compared to what is needed.
Yeah, and the counter argument to that is that we should put more effort into calculating analytic covariances on large scales, working out scaling effects for small simulations, working out better ways of using jackknife and bootstrap techniques. There are kind of a number of ways that we can improve on this. That is a different talk. I could give that talk if you want.
Well, I mean, that does sound nice, but I think it goes to your previous point of like, whenever you're doing kind of one thing on the large scales and another thing on the small scales and kind of pasting them together, you're sort of losing this very nice property that you've just extracted from the, from the prior. So
at least with this, you know what you're doing.
Yeah.
Or at least you think you know what you're doing.
That's the issue. Is the difference between those two statements. Okay, well, if they're, Peter's got another question.
Well, we'll use the magic words cosmic variance. So, how close or far away are we that's the big issue?
So certainly for EBOS, BOS, this has been like 10% at most, like increasing the errors by 10%. Obviously with things like DESI, Euclid, and the generation beyond, we're going way beyond that. And so, we'll have to wait and see. But I just don't think we're going to be in the situation where we're using this naive estimator for our covariances by just doing a straight calculation of the whole covariance from the simulations. I think we're going to have to do some sort of smoothing stroke modeling. And although Juna said she didn't like it, I think we're going to have some sort of hybrid stitching together of different techniques for it to work. Because I don't think we're going to get simulators to do more than like 5,000, 10,000 simulations at most. And then they get bored and go off and do something else.
Thank you.
Okay.
I just have a question. Is this accounting for parameter dependence in the covariance matrix? Where your covariance may depend on cosmological parameters?
No, it doesn't. That's a really good point. It doesn't. There are actually, I'm not too worried about that because I did some work on this and I'm going to dig out references for you. And what we'd found was that the approximations that the data were Gaussian were actually significantly or about the same order as the difference in the covariance matrix from different cosmological models. This is for BOS and EBOS tests. So if you want to worry about the covariance matrix actually having to change with cosmological models, you should worry more about the fact that your data is not Gaussian.
Okay, so that's not the limiting factor. Does that become true? Does that statement become less true as your data improves?
In general, we found not. I think there are two things there. One is if your covariance matrix and the simulations you run were not at your best fit location for your cosmological parameters, then you would worry. And you would probably want to convince your simulators to rerun the simulations or have some sort of scaling in there. But once you've got a single fixed covariance matrix at around or very close to, within errors, your best fit position, then all changing that covariance matrix with the cosmological parameters will be to increase or decrease your errors slightly. And looking at those changes, we actually found that it was, well, in one sense, equivalent to changing the form of your posterior. So instead of being Gaussian, quite often it becomes skewed if you're thinking like large-scale power spectrum, not quite being Gaussian, for example. And if you do that, then actually the skewness matters as much as the form or the model that you're putting into your covariance matrix. So I think, but perhaps I'm not answering your question. I'm saying, yes, perhaps it is important at a very low level, but there are other things that become important at the same low level as well.
Okay, all right, thank you.
Any more questions for Will? So if not, so let's stop the seminar here. And so